day 2 of CS50DC. Great to see all the familiar faces from yesterday, and hi to all the new people here as well. You guys didn't really miss out because all these lectures, as you can see, are recorded. So I'm just down behind here. So you guys can watch them on YouTube. Just type in CS50DC. I know some of you have watched it already, which is great. But if you haven't, just watch it over the weekend. It's about 40 minutes long. Today, we want to tackle, we want to talk about how a computer actually works. And this is a graphic that I'm going to explain to you. This should work. There we go. And we're going to talk about the different levels of a computer, and it's going to be visualized through this ladder. So if you're a user of a computer, you're going to be familiar with things like apps like Google Chrome or the calculator app over here. But you don't really know what's going on, how this app is actually working, how it's communicating with the computer itself. But we know for a fact that these apps are developed using these programming languages. For example, we've got Python and Scratch up here, and we're going to learn about Scratch later on today. But then you could ask, how do these programming languages actually work? How does the computer understand these programming languages? And then we can keep going deeper and deeper into the operating system and right down to the actual hardware of a computer. And today we're going to start right down here, explain step by step, going up, and by the end of today, you guys are actually going to have the tools using Scratch to create your own programs and build your own things on a computer. So let's begin right from the bottom with the actual hardware. Just out of interest, has anyone ever built their own computer or bought a computer and are familiar with some of the components of a computer? Yeah, so could you guys just shout out some parts of a computer that you guys know?
CPU.
CPU. Sorry?
Motherboard.
Motherboard.
Power supply.
Power supply.
RAM.
RAM, yeah. So these are all parts of the computer. And if we... yeah. So if we go back, let me get rid of this pen. We've actually got 2 motherboards in here, so we can actually pass this around. But as you can see, inside a computer case, this is what it actually looks like. We've got the motherboard stuck onto it, and all these different wires connecting these things. And we can see everything sort of connects to this circuit board called the motherboard. This is the kind of the central hub of a computer, and things like the RAM or the processor or hard drives or whatever all connect to this. So we mentioned the CPU. Do you know what that stands for? Central Processing Unit. And it actually lives inside here. And we're going to pass these around in a little bit so you can take a closer look at it. But this is all it is. And this is sort of the main brains or the nucleus of a computer. And this is where all the operations of a computer takes place. And if you guys are familiar with, if you've ever bought a computer or anything, you'll know that the performance of a CPU is measured in frequency. And for example, I don't know about this one, but the processor that I've got in my computer is 2.4 gigahertz. And what that means is that it can perform 2.4 billion operations every second, which is quite remarkable if you think about it. And really, if you guys have heard of Moore's Law, named after Intel's founder or co-founder Gordon Moore, it states that every 2 years, the number of transistors that you can fit on a little chip like this doubles, which essentially means that the computing power of a processor doubles every 2 years. So you get this kind of exponential increase in the power of a computer, which is why processors today are drastically faster and drastically more powerful than processors of 5 or 10 years ago. And you can really see the difference if you ever used a computer from 5 or 10 years ago. So this is the CPU, and we're going to talk more about how this actually works in a little bit. Someone mentioned RAM as well, right? And these are what clip on to here. Actually, I'll pass this around so you guys can take a look at it while I'm talking. Here we go. And these little strips, hello, these strips are called the RAM. And in this case, each strip is 1 gigabyte of RAM. So this particular computer has 2 gigabytes of RAM. And what RAM is, firstly, it stands for Random Access Memory. So it's a form of memory or storing things. And it's measured in gigabytes, as I said. And we sort of talked about what bits and bytes are yesterday. We talked about these binary zeros and ones. And a bit is really just short for a binary digit. It means either a 0 or a 1. And we talked about how 8 of these things, 8 of these zeros and ones, can be clumped together and called 1 byte. So 1 gigabyte, if you go right from the bottom, 1,024 bytes make up 1 kilobyte, 1,024 kilobytes makes up a megabyte, 1,024 megabyte makes up a gigabyte. So, if you think about it, approximately, what is it? in this 1 gig of RAM, around 1 billion bytes live in here. And if you think about it in terms of bits, you multiply it by 8. So within this small strip, 8 billion zeros and ones, or transistors, live inside it. And the same goes for this. I'm going to talk more about the difference between short-term memory, or temporary storage, versus permanent storage later on. But you guys can pass this around as well. So now that I brought up permanent storage, who can tell me an example of permanent storage of a component that, yes, Arnav?
ROM.
Sorry?
ROM.
ROM? ROM is actually a different type. Read-only. Is ROM the same as hard drive?
Yeah.
Yeah, well, another name, or we can, the more general name that people call it, the more conventional way of calling it, is the hard drive, which we have over here. And it is a form of ROM, or read-only memory, as opposed to random access memory. And this particular piece of permanent storage is called HDD, called a hard disk drive. And we couldn't actually get the screws to open it up, but if I did open it up, you'd see this disk here, which when turned on, would spin around and around at around 7,200 revolutions per minute, which is incredibly fast. But another form of permanent storage is called SSD, and it's becoming more and more prevalent, especially nowadays, because it's becoming a lot cheaper. And SSD stands for solid state memory, solid state drive. And the difference between an HDD and an SSD is that an HDD has a moving part. It has a mechanical disk that spins round and round, so it's louder, it heats up quicker, and it doesn't transfer data as quickly as an SSD, which is a solid state drive, so it's solid. It's completely still, no moving parts, so it's much quieter, it heats up a lot less, and it's much faster. And the difference, actually, between RAM and between short-term and long-term memory is that, I'll give an example here. Let's say you're writing an essay for your homework. So you open up Microsoft Word and you start typing in it. You haven't saved the file yet. So everything you're typing for now is saved in the RAM, in your short-term memory, or the temporary storage. But then once you actually hit that Control-S button and save that file, it'll be saved onto permanent storage. And the difference is, when you turn off your computer and turn it back on, if you've actually saved the file, the permanent storage remains there. So you can keep accessing the same files, but your temporary storage is completely wiped out and you can't access them again. So that's why we have to continue to save our files in case your computer crashes, because if you haven't saved it yet, it's in your temporary storage, so that information is lost. But for now, you guys can pass this around. Is that all, or have we talked about, can anybody think of any more?
Video card.
Video card, yeah, there's video cards, there's a graphics card, and that's actually inside the CPU. In this case, if you look at high-end gaming computers, you'll see a separate card, that's the dedicated graphics card, but that just makes sure that things like video or 3D objects or images are displayed correctly into the computer. But for now, those are the main parts of the computer, and those are all connected by the motherboard. But let's talk about the CPU in a little bit more depth and how that actually works. And we're going to look at an example where, let's say we're given two inputs, because a computer just takes an input, does an algorithm on it, gives an output. So let's say we have the numbers 4 and 5, and we simply want to add them. That's the algorithm that we want to perform, and we want to output the answer, which we know is 9. So in a computer, if you look at the CPU, it all begins there. If we kind of zoom into it, we'll actually see two different parts within a CPU. And that's called the control unit and the arithmetic logic unit, which is shortened to an ALU to be short. So let's imagine I'm a computer right now, I'm a control unit, the ALU is over there, and the RAM is over there. So I said we're given the two inputs, 4 and 5, and we want to add them, right? So it all begins with the control unit. I'd go over to the RAM to see all my data, because that's where all my data is stored. So I'd have the number 4 somewhere in my RAM, so I take the number 4, I'd have the number 5 somewhere here, I take it over here, and I have the instruction to add these numbers, and that's all stored within the RAM. So I have 4, the 5, and the instruction to add them. I take it back over here, and now I see I have to perform, I have to perform some math on them. So I go over to the arithmetic logic unit, and I give these 4 pieces of data, 4, 5, and the instruction to add. And now the arithmetic logic unit takes in these numbers, and this is where all the math happens. This is where, of course, these are all stored as binary, so the computer will perform the math on them in binary and get the result 9 and give it back over to the control unit. So from the ALU, you get the result 9. It goes back over to the control unit, and the control unit actually outputs the number 9 back to the user. So that's sort of basically how a computer works, or how a computer performs these many basic little tasks. And you guys will see that your algorithms are actually very, very complicated. You're not always just adding a number. But the thing with a computer is all these steps can be broken down into these very, very simple, basic steps that are performed extremely quickly by a processor. And this is the process by which that happens over here. But now, to understanding how a computer works, as I said, there's so much more than just the hardware, right? We're going to talk about the software and the operating system, how all of these things actually link in with the programming language, how this is read by the computer, and you guys can actually pass this around as well, just to look at it throughout the lecture. But for now, in order to understand better, not only the hardware, but how this links in with the software, and how this links in with the operating system of a computer, Murtaza is going to come up and talk about it.
Is this thing working? Right, so Ojin talked about all this hardware. He talked about the motherboard, the processor, the RAM, and the hard drive specifically. And we talked about how the instructions in the instructions are given to the processor from the memory and the data that it needs to work with, and then it just does operations with them and hands it back to the memory. But in order to actually understand how the instructions get there in the first place, we need to go a little bit higher in this ladder. So we talked a lot about hardware, which is the actual physical components that you can pass around. But these things now that are now coming higher up in the ladder are known as software, because there's nothing physical that's actually there. It's just a bunch of data or instructions or a program that actually makes the computer work. So this software, for example, these logos represent what? Does anyone know what they're called? Operating systems? Yeah? Okay. So we have Windows and OS X. Can anyone name any others? Yep. Any more? Android, yeah. iOS. These are also operating systems. But these would be desktop operating systems typically, and then iOS and Android work on mobile. So what the operating system does is the operating system is in charge of a lot of things. The first thing it does is make sure that any program that you're running on the computer has a space in memory. So that space in memory will have all the instructions for that program so that the processor can get those instructions from the memory and do stuff with them. And there's a part of the operating system known as the kernel, which deals with that. And another thing that the kernel deals with is handling inputs and outputs. So keyboard and mouse is usually the main thing that most users interact with a desktop PC using. So what happens is when a key is pressed, the kernel handles something called an interrupt. So whatever program is running gets interrupted, and this new information of what key is pressed is given to that program. And in order to handle this, the kernel uses a device driver to actually translate whatever electrical signal comes from the device into a software instruction. So whenever you're updating your drivers or anything, that's so that you can actually use your physical keyboard and mouse and have it interact with higher level software. So the operating system is in charge of all of these things. It actually makes sure that the processor knows what to do. It makes sure that the computer keeps running, because without it, the memory wouldn't be full of all the instructions that with all the programs that are running. Now, on top of that, we have programming languages. Up there, there's Python and Scratch. Can anyone name any others? Java, C++. So you guys have heard of these before. Now there's a wide variety of programming languages. They have different uses. There are some that are higher up in this ladder actually, and some that are lower down. So something like C would be quite low down in that ladder, whereas something like Scratch is quite high up. This basically means that certain programming languages talk more directly to the hardware than others. So they're closer to the metal, we say, or lower level. What these programming languages do is they translate what a user writes or what a developer writes into machine code, into binary. So in order for as we said yesterday, computers work only in zeros and ones. So obviously we can't just type words and have the processor understand them. We need to somehow convert them into binary that the processor understands. Now Ojin talked about how you would pull the instruction from the memory. That memory, that instruction would be formatted as some string of ones, some sequence of ones and zeros that the processor understands. So what actually happens with a programming language is that it's compiled into those ones and zeros from what the user has written. There are other programming languages that actually aren't compiled straight away. They're compiled, they go further down the ladder until they can actually get to machine code. But essentially what the programming language does is allows a programmer to write code without having to actually literally write ones and zeros. And this, without this, it would basically be impossible to write any complicated program. And with that, finally, we get the applications that we actually use. Now this type of software is called application software. The software that we talked about lower down is system software. It deals with actually controlling the computer. It deals with organizing the devices and organizing the memory, making sure that everything is running smoothly within the system. Whereas these applications at the top, Chrome and Calculator and other apps like Microsoft Word or any other thing that most users would use, these are called application software. And they're written in a programming language. So the person who writes those apps doesn't actually have to write any ones and zeros directly. And they help the user to do specific tasks. So these are the actual useful parts of a computer. They let us do things. Like the calculator is where you'd actually type 4 + 5 = and to get 9. So that's really where most users actually interact with the computer. Now, there is an analogy that we can use to understand the computer. So we have Chef Ramsay over here. We can think of Chef Ramsay as a processor, because he is the one doing everything in a kitchen. He is the one who's controlling all the ingredients, putting them together, doing operations on inputs. So a processor would add 4 and 5 to make 9. Gordon Ramsay might add like flour and sugar to make a cake. You can think of his tables, his counters, as RAM. So this is where he puts stuff that he's working with. He puts things in temporary storage so that he can easily access them and do things with them. If for some reason he's gone mad, he might actually use a recipe there, like an instruction in RAM. So he would put anything he's working with on a counter, which can be thought of as RAM. The permanent storage then would be the cupboards that he keeps his ingredients in over the long term. So essentially, he would get his ingredients out of the cupboards when he needs them, as a computer would take data out of a hard drive. He would put them in the RAM or on the counter, work with them, so do a process on them, and then produce an output, and then probably put it back into the cupboard if he's done with it. So this analogy for a computer actually shows quite well how everything works together. You could even extend it to the entire restaurant, where you could think of the waiters as applications that are requesting things from the kitchen. They're requesting certain operations to be performed, like someone over there might order a cake that Chef Ramsay has to make. And then you can see this guy, you can see the waiter over here as the operating system. It's the interface between the user, essentially, and the applications and the hardware, the lower level hardware. So it actually listens to what the applications want and makes sure that Chef Ramsay and his kitchen have enough time, have enough space to make all these things. So this is a pretty good analogy of a computer, but obviously it's still an analogy. So when we're thinking about a computer, we can kind of think of it like this, but really it's quite different. There are more steps in the ladder that haven't been put there, like the programming languages don't really fit in there, which are actually quite important in a computer itself. I think that's a good place to start with understanding the structure of a computer. And I think now Mr. Wood is going to talk specifically about programming.
Yeah, thank you, Mutaza. We'll edit that bit out. Okay, right. I think that was an excellent analogy. With regards to these sessions, we do our own little bit. We talk about what each person's going to talk about. Well, that was really well explained. I thought that was fantastic. Hold on. Right. So what I'm going to do now is, if we talk about this ladder, and I'd stand over here quite a bit, I think. If we talk about this ladder, Ocean's talked about this. Mutaza's talked about this stage here and how everything comes together. We now are going to start straight away. I told you this was going to be fast-paced. We're going to dive straight in. I said that in the last lecture. We are now going to talk about these programming languages. And today I'm going to set your first problem set. So the idea of engaging in these lectures is not only to just stand here and be lectured. but we run a Monday session as well for a workshop where we are going to set you problems every week to go away and solve. And the lectures are going to guide you towards how you might solve those problems. And if you are submitting work for the AP accreditation, for those of you that are interested in that, then you will need to complete these problem sets. You have to complete these problem sets. For those of you that are here to just engage in the learning and aren't too worried about the AP, then these are here to also engage you, and we would ask that you put some time into it, that hopefully you're here because you've got an interest in it, so putting time into something you're interested in isn't that big of a deal. So we do want commitment. We've got your commitment by you coming to these lectures, but we'd also like you to put, like I say, some time into the problem sets that we're going to give you. So what we're going to do with the first problem set is we're going to level the playing field a little bit, because when Murtaza was talking about this, I was sat there thinking, wow, what a great analogy. I can contextualize all of that. I know about a lot of this stuff in here, and that just gives me a much better sort of general overview of it in terms of what others might understand, especially when I go into teaching this to year 7, which we do now. The first topic in year 7 is understanding computers, and we do all of this, we rip them apart. And I've never seen this analogy, and I'll use it. But when I was sat there thinking about it, I thought, well, I know about this, and that analogy has helped me. But for some of you, it still might be a little bit confusing. And with regards to the programming languages that we want you to use as early as next week, Murtaza talked about how, well, even the programming languages themselves can be put on this ladder. Certain languages will be lower. We call them low-level programming languages, like C. Very low-level programming language. And some of them will be a lot higher, like Scratch is right up there at the top. It's called a blocky programming language. And Python sits around about the middle. So what we need to do is we need to level this playing field so that everyone in here is starting basically at the same point. So even though next week we're going to be introducing code like this, which is C, it kind of gets a little bit daunting. It's very syntactical, it's very text-based. You know, we've got things there like a hashtag, and we've got things here like a semicolon and a backslash and some parentheses with curly brackets, and it's like, whoa, what does all that mean? It can get quite confusing quite quickly. But actually, it's not actually that too difficult to interpret. And again, just to check that I'm not patronizing you, has anybody written in C before? Put your hand up if you have written in C before. So there's 2 of you. Possibly 3, possibly 4. We've got quite a few people here today, so there's a lot of you who haven't. So if you didn't put your hand up then, so there should be about 15 of you who didn't put your hand up then, can you have a look at this and tell me what you think it will do when I execute this program? Anybody who didn't put their hand up then, what do you think it will do? Robbie, what do you think it will do? When I run this program, what do you think it will do?
Hello world.
There you go, and that's exactly what it will do. So although it's got all this sort of syntactical context of, again, like I've said, all of this sort of, what are these hashtags, we can still actually interpret it. Yeah, we can still look at that and say, well, you know what, it's probably going to do that. And I'll be worried about these if main voids and stuff later on. But yeah, fundamentally, that's what that program will do. But to level the playing field, we're going to do your first problem set, or we're going to set the first problem set to use Scratch. We want you to use Scratch, and here's the reason why. What Scratch does is it lets you forget about all of this possible complexity. Although Robbie was able to interpret that, like I said, we've got to make sure we don't make any syntactical mistakes when we use a text-based programming language. And to make sure that's not the concern, and what we're bringing the focus to, is this idea of solving problems and the idea of computational thinking and not having to worry about syntax. Scratch is great for that. Scratch is a programming language and an application developed by MIT. It's fantastic. I started using it several years ago, and it's got better and better and better. We're now a web version of the application where you can create online. So for those of you that have maybe experienced Scratch before, give it a chance. There's some great stuff in here, and it will take away that idea of complexity in terms of syntax and draw you into computational thinking and problem solving. And that's what it's going to do. So what I'm going to do now is I'm just going to give you a little overview as to what you can do in Scratch. So first of all, when we look back at this program here in C, this does exactly the same as this. So if in Scratch, which is a blocky-based programming language, if I wanted my application to say hello world, I just drag these two little blocks together. Whereas if I want to do exactly the same thing in C, I'd have to write these 5 lines of code. So in Scratch you can do everything that you can do in all other programming languages. And you'll see throughout this course that a lot of these words will reappear because these are the fundamentals of a programming language, of any programming language. We've got functions, loops, variables, Boolean expressions, conditions, arrays, threads and events. And if you've done any programming, you've probably heard at least one of those being said before. If you haven't done much programming, or you have done a lot of programming, by the end of these lectures and by the end of these problem sets, you will know a lot more about each of those in a variety of programming languages. So, we'll start with this one. This in Scratch is a function. This is a function. It's saying basically, when I use that block, I'm going to pass this function called say, the parameters hello world, and then this say function will just execute something that will make my screen say hello world. Not audibly, but text-based. So this is a function, I pass it some parameters, and it will say hello world. That was a function. The next one. This here is a loop. This is a forever loop. This will do whatever is inside this forever block here forever. So if I use that in this blocky programming language called Scratch, it will continuously say hello world forever, which is a bit of a white lie, and we'll see why in our next lecture, because actually computers they have a certain amount of memory, so they are actually finite, they're not infinite. You can't do something forever. At some point it will stop, and that point will be when you've run out of memory. We have these, which are another type of loop. These loops we call a definite loop. We know definitely that we want to do something 50 times. We don't want it to do it forever. We don't want it to do it twice, although we could by changing the parameter here. We want to do something 50 times. What do we want to do? We want to run this function that says hello world 50 times. These here are what we call variables. So here I'm creating a variable. So you've probably heard variables before, maths maybe. Variable is something that can change. And what we're doing here is we're assigning a variable called I. We're assigning it the value 0. So I'm creating this little place in memory. I'm saying call that place in memory I and put 0 in it, and then I might want to do something with that variable later on. And I'm just going to whiz through these now. This is called a Boolean expression. This is saying if what is in I is less than 50, then I might want to do something. So a Boolean expression will either equate to true or false, or like we were talking in the last lecture, a 1 for true, a 0 for false. This is a Boolean expression using variables, so rather than putting in a constant, I might want x and y to change. These are very useful and something that you'll be expected to use in your first problem set. These are conditions. So this is using these Boolean expressions within a condition. If this Boolean expression is true, then do this. Else, if this Boolean expression is true, do this. Else, if neither of those are true, do something else. These are called arrays. This is where, if we talked about variables previously, a variable can store one piece of data, either a number or a piece of text. A list, which is another name for an array, is where I can store many pieces of data in one variable. So I might want to store someone's name and age, etc., and not just their age. So these are arrays. We'll be using those. This is called threading. A lot of computers nowadays, a lot of things you guys use, you don't just do one thing. You can have several things going on. You might be in Google Chrome downloading something from the web, and at the same time you might be in Microsoft Word writing up some homework. So you're doing two things at the same time, and computers can do that. And that's called threading, multi-threading, where we have two things going on at the same time. We'll be able to do that in Scratch very easily. It can be a little bit more complex when you're using the textual-based programming languages, but in Scratch it makes it very easy. These are called events. This is where I might want something to happen at a certain point in my program, and I can trigger these events by using these broadcasts here. I won't elaborate too much on those. And then finally, for those of you that have used Scratch before but might not have used it for quite a while, it's got a new feature here where we can actually create our own blocks. So say if MIT missed something out that you want it to do, we can create our own functions, as it were. So we can create our own say function if we wanted to. And I'm going to elaborate on how we do all of these in just a minute. So, here's what I thought I'd do. What I thought I'd do is I'd show you, the reason we are doing the CS50 course is because myself, Mataza, Ocean, and I know a couple of other people in here, especially if you're doing A-level computer science, is that there is a course online called the CS50X course. Yeah, that is Harvard University's Introduction to Computer Science that you can take online. And several of us in this room have done it already, or not finished it, or started it, or some have finished it. And for that Harvard University course, the very first problem set, if you go to Harvard University and do their computer science course, is the same problem set I'm giving you. And I've done that, and I'm going to show you what I submitted for my problem set for this problem. So this is my result. It got marked, it passed. So I know that this is actually an okay Scratch project to show you. I know it passed. This is my game that I submitted, and you'll be all expected to do this for the problem set. You will create your game. You will upload it to the Scratch website so we can all go and play it. So, would anyone like to come and play my game? There's a free duck in it for anyone who wants a new duck. Oh, look at those hands go. Matt, come on, come down. They were apprehensive until I told them there was a duck. Right, so Matt, if you just make the screen big. Yeah. I'll tell you what I'm not going to do. I'm not going to explain what you've got to do, and then otherwise I'll see whether my game's good. It did say press the space bar to move, if you didn't see that before. Oh. So what do you think you've got to do, Matt?
I'm guessing that it goes in the direction it's pointing.
Okay, so what if you keep hold of the space bar? Oh. Oh. Oh, well, that's pretty good. So notice I've got lives up there. I've got a sprite. The sprite is the thing that Matt's moving and controlling. Oh, and I've got events. I've got an event that says when something happens, do something else. When this sprite touches that arrow, ooh, what have you got to do now, do you think?
I'm guessing that's something I could collect.
Well, Matt, let's just try going to the arrow without collecting it. And you'll notice that I've actually got a couple of conditions going on here as well. For example, if Matt gets to the arrow, if Matt gets to the arrow, if he ever gets to the arrow, one day we will find out whether if he gets to the arrow, he's going to be frustrated. Because if he gets to the arrow and he hasn't collected this, then he can't go to the next event. Also, you notice that if he touches this green, he has to start back over again and he loses a life. So all of those things that I showed you at the start, this idea of functions, conditions, etc. There's a lot going on in here. I was quite pleased with this game. It is quite addictive. You had to collect the C on this level, the S on the next level, the 5 on the next level, and the 0 on the next, CS50. Feel free to go and play with Matt. There you go, well done. He wants to stay, doesn't he? He wants to stay, well done. If you want to play that game, all you've actually got to do is go to the MIT Scratch online, and if you just type in Mark_Wood, you can actually play my game. It's this one here. So if you want to have a look at that, feel free to go and have a look at that. So I just want to give you a bit of insight as to the process that I personally went through when creating this. So that's what I'm expecting from you for your first problem set. But I want to give you a bit of insight into well, how did I come up with that? what did I do when I came up with that? And this is a great example of decomposition, which is a very important aspect of problem solving. Some problems that you're going to be asked to solve throughout this course are very, very big, can be very, very daunting. And so what you do is you break it down into small little chunks. And you say, well, I'm going to take baby steps. I'm going to break this down and I'm going to do one little thing at a time. So for me, when I created that game, I had an idea about what I wanted to do, and then I procrastinated for a very long time, creating the little graphics, creating the stage, and then changing my mind and changing my idea, and oh, I'll make that CS50, and I did that for a while. So get that out of the way. You will start designing your game and you will procrastinate a lot. Get off of Facebook, get off of going to look at the Daily Mail website, and focus down on, right, this is what I want my game to do, and then break that into small chunks. So the first thing I wanted to do is, right, I know that I wanted my sprite to spin. I know I wanted to do that. The sprite is the object that Matt was controlling. I know I wanted to do that. So all I did is I created a little program where I had a little sprite on there, and I just see if I could make it spin. So that's the first thing I did. I did that, and I managed to do it, and then I came up with the next thing. So I decomposed the next problem I wanted to solve, and I wanted it to move in a certain direction. So notice when it was spinning, it would only move in the direction where its nose was pointing. So I then focused on, right, well, how the heck do I do that? So I broke that down, and I actually created another little Scratch game. So I had Scratch version 1 that was literally just a sprite spinning around. Then I created another one that was Scratch version 2 with the sprite spinning around, but I could actually then make it move. And I'm decomposing this big problem that I had into smaller chunks. And it's a great bit of advice for the problem sets that you're going to have throughout this course. Then what I wanted to do is trigger an action, because I got it to spin, and I got it to move, and I thought, right, well, I want to bump into things, because if you don't follow the maze, I want it to go back to the start. So I actually created a whole new game where there was no sprite spinning, there was only a sprite moving, and I just thought, right, how do I make it so that if I hit the edge, it goes back to a certain point? So then at this point, I actually had 3 games going on, each doing their own little thing. Then I wanted to trigger on a different action if it bumps into the arrow, because that was different. If you bumped into the green, that was just sending the sprite back to the start. But if you bumped into the arrow, I wanted to change the whole level. I wanted to go to another level. So again, I created a 5th project that all it did is have a sprite that touched an item and it changed your background. That was it. So at this point, I actually had 5 games going. Then I got into it. Then I started understanding how this all worked, how I would get things done, etc., etc. There's nothing more to be said by you guys. And so what I did then is I started building the levels. So I knew how to take it from one event to the next, so I just started building the levels. And then I introduced lives. It was a little bit trickier actually than I'd anticipated. The lives was this idea of having a variable that stored the lives and deducting them. And it actually isn't that complicated, but I got it a little bit wrong because the lives variable needed to be seen by everything, not just the sprite. But you'll understand what I mean when you start going to play. And then it just went on from there. So decomposing this, what may seem like a big problem to some and a simple problem to others, is a good piece of advice. So, this is Scratch. That's going to be your problem set. I'm going to show you where the problem set lies. So where do you actually go and read what the problem set is? So if you've got a piece of paper, please take notes. If you haven't got a piece of paper, what I will do, hopefully you've all accessed the YouTube channel by now, what I will do is I'll post this lecture on YouTube, and in the description I'll actually put a link to the piece set. Okay? But this is where it lies. It lies here, on that URL. If you just make a note of that, and then I'm going to show it you. So take a picture or make a note, and then I'll show you what the problem set looks like, because again, the problem set itself can be a little bit daunting. This is what it looks like. And you need to get familiar with this quite quickly, because this is what all the problem sets look like. There's a lot of reading. We have an academic honesty policy that's come straight from Harvard University. So these are not our problem sets. We have not come up with these. These are Harvard University's problem sets. And they're presented by them. They have an academic honesty policy. What's reasonable, what's not. This is how it's going to be assessed. Then it gives you a bit of background on what we've covered in this week's lectures. So we're talking about binary. We're talking about ASCII, which is what we covered in the last lecture in case you missed it. There's a nice few links here to sort of hardware stuff that Ocean was talking about. Then it dives into, right, Scratch, what is it all about? This is David Mallon. If you don't know David Mallon, he's the guy who developed, or is actually running the CS50 course over at Harvard University. Then there's a bit more detail here about Scratch and how you can use it, how to access it. Some few little shorts here. These are nice little short clips of, if you're having any problems, consider this. And you can see that this is a bit of information about the team that developed it at MIT, etc., etc. Now, where's the actual problem itself? This is it. And here's the criteria. Your time to choose your own adventure, and your criteria, your project must have at least 2 sprites, at least one of which resembles something other than a cat. Your project must have at least 3 scripts in total. Your project must use at least 1 condition, 1 loop, 1 variable. Your project must use at least 1 sound. Your project should be more complex than some basic examples. So there's the criteria you got to meet. Does anybody have any questions about Scratch? No? 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 Okay, so just to finish. Oh, that's a nice little view. Just to finish, I'm just going to very quickly show you this website, right? And I'm going to show you how to use it. When we mark them, we're going to run them through this before we mark them. Let me show you this website so that you can actually go and access it. I'll put a link on the YouTube channel to this as well. What this does is you can go to any Scratch project on the MIT website. So for example, is this mine? No, this one is not mine. If I go back to mine, just give me 1 more minute. If I just type in mark_wood, what's really nice about this is that because it's all it's the idea of being collaborative with Scratch, you can actually go and click on see inside and see all the code that makes this game. That's my game. You can then actually go to File, and you can download this game to your computer if you want to open it in Scratch, if you have the desktop version of Scratch. I'm going to save this on my desktop. Watch what I'm then going to do. I'm going to go back here. I'm going to upload that Scratch project that I've just downloaded onto my desktop, which should be under Mark here. And then I'm going to run it through this analytics software here that will actually analyze how good my Scratch project is out of 21. So how much abstraction there is. If you don't know what abstraction is, I'll show you a nice little tool in a minute. So my score gets, my game gets 16 out of 21. Okay, what I want from everybody is that you are all masters. Yeah, master is 15 and above. Okay? If you want to know how you improve these, and you want to know what flow control is, click on flow control and it'll tell you how you would get 0 points, 1 point, 2 points. This is how you can make your games better. Okay? Guys, that was CS50, week 1, lecture 2. Hope you enjoyed it. Take care.